Welcome to the beginning of our second unit where we're going to be talking about kinematics. Now kinematics is basically just all about motion, which starts with uniform motion, which we covered in grade 10, but let's just do a quick review of some definitions and a couple of equations. So let's start off here with distance. The SI unit is meters, its symbol is a lowercase d, and the definition is the amount of space traveled by a given object. Now there's no vector arrow with the symbol, so that does indicate that this is indeed a scalar value. Position, SI unit, is meters. Its symbol is lowercase d, but this time it has a vector arrow over top. So as the definition says, it is a vector that indicates the location of an object from a given reference point. Now the reference point could be the origin for just regular coordinate system, but reference point is just more general because it can be from any point. So let's go on to displacement, SI unit, meters as well. Symbol, lowercase d, vector arrow with the Greek letter delta out front of it. Now that stands for change in, the Greek letter delta. So as the definition says, it is a vector change in position. So it is the vector change in position, which can also be understood as the straight line distance between two positions irrelevant of the actual path. Now there's our equation for this. So we've got delta d, displacement, is d minus d0, which both are position vectors. Now last year we saw this is df minus di. Now instead of using f and I, we're going to use d0 representing di. So d0 or d0 represents our initial, and then just no subscripts will represent our final. Now this is just to be consistent with future equations that will involve initial and final velocities or displacements. Time interval, SI unit, seconds. So it is not minutes or hours, it is indeed seconds. Time interval symbol, delta t, and we'll define it as the length of time. I know we shouldn't use time in the definition, but it just it fits, and I think it's something we all understand. The length of time during which an event takes place. And we'd have an equation, delta t equals t minus t naught. And I'm going to put a little caveat in here. From here on, use t instead of delta t. Now that's just because physicists are lazy. We are assuming that t in all of our equations represents time interval, so we just decide not to write it because it's an assumption that we make. Let's look at this example. So at t equals 0 seconds, I'm at my office. So I'm going to do the picture as I read it out here. So draw a picture. I'm starting here. we can say that that is t equals 0 seconds. And I go 10 meters north in the 5 seconds there. So I'm going to end up somewhere up here. I've gone north, and this is time equals 5 seconds. And at time equals 10 seconds, I turned around, so I went this way. I came back 4 meters south, and I ended up here. So this is time equals 10 seconds. And then I end up all the way back at the beginning here. Time equals 15 seconds. And then so finally I walk to the car in the parking lot. It should say at time equals 20 seconds. So that's going to be over here at t equals 20 seconds. Let's take a look at these couple of questions here. What was my position at time is 10 seconds? Well, I had gone 10 meters and I went back 6. So my position, I went back 4. So my position is that we're 6 meters north. So let's go with position equals 6 meters north. What is my displacement between 0 and 10 seconds? Well, let's write out a quick equation. Delta t, delta d is d minus d naught. And my final is 6 meters north that I just figured out, minus my initial, which is 0 meters. So in this case, it ends up being the same as my position. What was the total distance I traveled after 15 seconds? So total distance, I'm not going to have direction. I went 10 meters, then I moved back 4, and I went all the way back to my office. So that's 10 meters both directions. So my distance for this answer is 20 meters with no direction. And what is my displacement between 5 seconds and 20 seconds? I'm going to leave this one for you guys to do, and we'll take it up in class. Let's talk about uniform motion. Objects in uniform motion, when they travel, equal displacements in equal time. Objects that are in uniform motion don't do 3 things, and that would be speed up, slow down, or change direction. The change direction part we'll get into a little bit later, but most of the time we are dealing with speeding up or slowing down when we talk about acceleration. And that will be after a couple of days from now. So let's talk about speed and velocity. Now we can't really do much without these two things and being able to calculate them. So they are different, and let's just go over the subtle differences between them. Meters per second are units in both. So we can go ahead and write that in there. Our symbol for speed is just a lowercase v, and as the definition indicates, it is a scalar quantity representing the rate at which an object covers distance. Now that's key here, and that will show up in our equation and our examples. So our equation here, so speed equals distance over time. No vector arrows, none of these are vectors, they are all scalar values. Let's talk about velocity. So velocity, symbol, lowercase v, as you might have guessed, it is a vector, so it gets a vector arrow, and it is a vector quantity representing the rate at which an object covers its displacement. So that's that's the key, displacement versus distance for velocity versus speed. So let's write out our equation. Velocity equals delta d with our vector arrow over time. So that's the key. They're very, very similar, but they will end up being different values. So let's take a look at the first example we'll set it up and I'll leave the calculations to go over in class. So I ride the bicycle 12 kilometers east in 36 minutes, then turn around and ride 5 kilometers west in 24 minutes. So let's go over, so our distance, 12 kilometers plus 5 kilometers, so that gives us 17 total kilometers. Time, well, 36 minutes plus 24 hours, so that's 60 minutes, which we can also write as 1 hour. So we can get our answer into kilometers an hour, a little better than kilometers a minute. So that's that. And the only other one that we would need is our displacement. So our displacement would be our initial, if we're going with the definition, is our final position minus our initial position. Well, we're assuming our initial position is our reference point here. So that is 0. And we just need to figure out how far away we are from that. This one, it's easier sometimes to draw a picture. So if we went 12 kilometers east and then we went back 5 kilometers, that means we ended up at 7 kilometers east. So with those, calculate the speed and velocity for the trip, and also take a look at number 2 prior to next class.